Okay. So yeah, this was the first question that was given in the worksheet. Long hollow cylindrical wire of radius r carrying a current I. The current I is distributed uniformly on its surface and it is flowing along the length of the wire in a direction parallel to its axis. Derive the net magnetic field produced by this current at any point on its axis. Okay. Now it's an infinitely long hollow cylinder of which a part has been shown to you. So tell me, did any of you try to solve this question? How did you, or if you have an answer, you can tell. Any ideas? We need to find out the net magnetic field that it produces at any point on its axis. Let's consider this. Let me mark a point here, P, on the axis of the cylinder. How to calculate the magnetic field there? Okay.
Mu naught I by 2 pi r.
Mu
Or 2
naught.
r. Mu naught I by 2 r.
You are saying it will be mu naught I by 2r. Why do you think it will be mu naught I by 2r?
I didn't know what to take as the element in this question. I thought we can consider it as a collection of coils.
Are there any turns you see here? Like if you imagine the flow of current, okay, any one electron's movement you take, in which direction are the electrons moving?
Opposite to the direction of current.
Opposite to the direction of current. Yes. So if current is flowing upward like this, that means electrons are going like this. So if you track the motion of one electron, it will be going this way. Another electron may be moving here along this path effectively. So they're moving in straight lines, right? So the current is also flowing in straight lines here. These are not turns. Okay, so this is not like a coil. You can't consider the system like coils. Any other idea? Or now that I told you that currents are flowing in straight lines, do you have any idea how to solve? Have we discussed anything about the magnetic field produced by a long straight current or not?
Yeah.
We have. Okay. If there is an infinitely long, just a moment. If there's an infinitely long straight current carrying wire, let's say it carries a current I. Shashank, you tell me, how much is the magnetic field it creates at a distance x from itself?
Mu naught I by 2 pi x.
Mu naught I by 2 pi x, correct. Okay. And what is the way to determine the direction of the magnetic field?
Put your thumb along the direction of current.
You use the right hand thumb rule, correct. You use the right hand thumb rule, fine. In this particular case, the diagram that I have drawn on the right side, what is the direction of magnetic field at this point P? Into the screen, correct. Okay, fine. So we know something about straight currents. We know something about magnetic fields produced by straight currents. Now the current flowing in this on the surface of this hollow cylinder, okay, is a collection of many straight currents like this. Are you able to look at it that way or not? Isha, what do you say? Is it a collection of straight currents or not?
Yes, sir.
It is. Okay. So what we can do is we can take one of those straight currents, find out how much field and in which direction it produces the field on the axis. Then we can generalize it for all the currents. Do you think any point on the axis will be equidistant from those currents or not? Shashank, what do you say?
Yes.
Any point on the axis of the cylinder will be equidistant to all these currents that are flowing on the surface of the cylinder. Okay. They all together are equal to I. Okay, individual currents are not I, but the total current is I. So what we'll do is we'll consider an element first, some part, okay, of this cylinder surface. Let's say this section. Now you can see there's a current flowing there in that section, some current flowing there like this. Let's consider that it's a straight current. Okay. So the current direction is shown by the arrow. I'll just draw it a little longer. Just a moment. Let this be the current. So you can see the current direction. You can see the point P where we want to find out the magnetic field. Now, both of you try and tell me the direction of the magnetic field that green colored current creates at point P. What is the direction of magnetic field created by that current at the point P?
Outwards.
Outwards. Okay. Not exactly outwards. It would be at an angle like this. Out of the screen only, but not straight towards you, at an angle like this, because right hand thumb rule, you'll have to place your right hand finger. Okay. It depends on which thumb rule you are using. Suppose you place your thumb this way and your fingers this way towards the point. Then the palm will be facing towards you, but it will be at an angle. Okay, so it's like it'll be in this direction. The palm will be pointed in that direction. So the magnetic field created by that green current at the point P is somewhat at an angle like this. It creates a small magnetic field. Let's call it dB because the current is di. It's not that, I mean, total current is not in that green one. Okay. Total current is I. Some part of the current flows along that path. Okay. So it creates a magnetic field like this. It's actually in the radial direction of the cylinder. Okay. You can visualize the top view. Let me help you with the top view. Just a moment. If you look at it from above, it looks like a circle. And there are currents flowing towards you. So all these dots inside circles, they represent current towards you. What we did was we considered one of those currents and we visualized the magnetic field that it produces at the center. Now current is towards you, the point is downwards. So it's like you'll have to place the thumb this way, out perpendicular to your screen. You have to place the thumb this way, thumb down, and then the magnetic field that it produces points in this direction. It's along the radius. Okay. Now consider another element. Some random element we will take. Let's say this one. I'm marking it in red. Okay. Now the green one is done. It had some current di. Now the red one, it has some current di. From the red one to the center. Okay, the point P where we want the field is here. So if you do, I mean, if you apply right hand thumb rule, you will see that the field produced by that red current points this way. Will these two fields have the same strength or different strength? You were told in the question that the current is spread uniformly on that cylindrical surface. So will each current create the same amount of field at the axis or not?
Yes.
It will. Current strength is same, distance is same. So the magnetic field strength should be same. Okay. Similarly, you take other elements. Say you take some current here at the bottommost point. Okay. Current is towards you, point is upward. Isha, can you tell the direction of magnetic field created by that blue current? Current is towards you, point is upwards. So you'll have to place your right hand thumb towards you and make your fingers point upward. Which way is your palm facing?
Sir, towards left.
To the left. Correct. Correct. So you get one magnetic field like this, dB. It will also have the same strength as the others. So if you combine the effect of all these magnetic fields now. You will have many other magnetic fields, one pointing like this, one pointing like this, okay, one in this direction, and so on. There'll be a magnetic field in every direction because there is a current on in every direction. So now tell me, what will be the resultant of all these magnetic fields? They're all of the same strength and you have fields in every direction. What will the net field be?
0.
0. Net magnetic field on the axis will simply become 0. Okay, that's correct. Okay, so here if you visualize that green current is producing field this way, opposite to it on the other side, if you take a red current like this, it will produce magnetic field in the exact opposite direction to the green one's field. Those two will cancel. Okay, likewise, every element has another element opposite whose magnetic field will cancel this one's magnetic field. Net magnetic field anywhere on the axis of that cylindrical wire becomes 0. Okay. Now let's solve the second question. It is related to the first question. In the second question, you are given a half cylinder, okay, or as I wrote there, semi-cylinder. And you had to find out the net magnetic field at a point on its axis. Now let us take the top view of this. If you look at it from above, it will be a semicircle. So let me remove half of it. Okay, and there are currents everywhere flowing towards you. Each current is di, total current is I. Okay, they're all towards you. And we need the net magnetic field at a point on its axis. So at this point. Okay. Let's consider that first current element. You can't call them elements. Let's call this current as di. Okay, so in the diagram, in the left side diagram, you can see it is this current that I'm referring to. Di. We know the direction in which it creates the magnetic field. It will be this way. So in this diagram, di is towards you, point P is downwards. So thumb should be pointed upwards, finger should be towards you. Then the palm will face towards left, towards right, your right. So this di will create a small magnetic field dB like this. Next, consider some other element, maybe not element, some other current, small current, maybe this one, di. Di is towards you, fingers will be pointed towards P, thumb towards you and fingers towards P. The palm will now face this way. Okay, consider some other current, maybe on the lower side. This one. Di towards you, thumb towards you, fingers towards the point. Palm will now be angled like this, oriented this way. Right. And the last element on this side, if you take thumb towards you, pointed, fingers pointed upwards towards the point P, then its magnetic field will be like this. Okay. So in between also you will have infinite other vectors because there are currents flowing. You have currents flowing in every direction. There'll be vectors in different directions. There'll be magnetic field vectors in different directions. Now you all visualize first. What is the direction of net field going to be? All these small magnetic fields will be of the same strength. Okay. And you know how they are directed. You imagine a bunch of magnetic fields like that. What do you think will be the resultant's direction? Yash, can you tell? It's like a bunch of vectors in the first and second quadrants. Okay. They are all of the same strength and they are distributed in every direction. What will be the direction of the resultant?
Sir, I think so. The only green one will be there, sir.
A green one has a red one opposite to it. It will cancel. Shashank, Isha, any answer? Okay. Just consider two vectors like this. Let's say these are the first and second quadrants. One vector this way, making an angle alpha. Another vector this way, making the same angle alpha. If their strengths are same, what is the direction of their resultant? What is the direction of their?
Along that along the y-axis.
Along the y-axis, it will be exactly between them. Okay. Two vectors of equal magnitude, their resultant will always be along their angular bisector. Okay. Now in this question, it's not just two magnetic fields that we have infinite number of magnetic fields. But you see there is a symmetry, right? How many ever vectors you have on the left side of y-axis, the same number you have on the right side of y-axis. So what do you think will be the direction of resultant of that bunch of vectors? Anyone?
Along the y-axis.
It will be along the y-axis. Okay. So in this case, the net field is going to be this way. Now, why is it important to get the direction of the net field first? Now see, the question is to calculate the net magnetic field on the axis of that half cylinder, cut cylinder. Net magnetic field is the sum of individual magnetic fields, and magnetic fields are vector quantities, and there are infinite small vectors that you have to add here. So you'll have to integrate something. You'll have to integrate a vector quantity. So you'll have to take components. Now, if you can visualize what the direction of the net field is going to be, you can only integrate components along that direction, and that will be enough. Okay, you don't have to bother about the other component. So that's how you should proceed in such questions. Okay. So what we need now, at least the steps are clear for us. We need to write an expression for dB first. Then we have to take the y component of dB. And then the last thing we need to do is integrate the y component of dB to get the net magnetic field in the y direction. These are the steps we need to take. Okay. Can any of you tell me how to write an equation for dB, the small magnetic field produced by one stream of current, not the total current I? That is the question. You have to find out the field produced by total current I, but one stream of current, how much magnetic field it produces, how will you write? Let's consider that, which one shall we do? Let's consider that blue one. I'll erase the other vectors. Because usually when you are integrating, when you are deriving an expression that needs to be integrated, you should never take the first element or the last element. You should take a random element in between. Limits will be from first to last. Okay. So let's consider that blue element that we have taken, blue stream of current. We know it creates some magnetic field dB this way. Or in the diagram, if you visualize, diagram on the left side, just a moment. Let's assume this is the stream of current that we are considering. That stream of current creates a magnetic field this way. How to write an expression for dB? Let's visualize the x and y axis also. Okay, What kind of current is it? Is it a straight current or a turning current?
Right.
Straight current. What is the formula for? And is it infinitely long or finite?
Infinite.
Infinite. It's a long hollow semicylinder, so you'll assume it is long enough to be called infinite. What is the formula for magnetic field produced by an infinite straight current at a distance r from it?
Mu naught di by 2 pi r.
Okay. If the current is I, you will write mu naught I by 2 pi r. If it is di, you will write mu naught di by 2 pi r. Correct. Good. Here, r is the radius of that hollow cylinder. Okay. It's effectively the distance from the surface of the cylinder to the point where you want the magnetic field. Correct. Now we need to take these things y component. For components, we need angles. Let's call this angle as theta. Then, since we took angle with y-axis itself, okay, you should call this dB, small magnetic field. Then dB's y component becomes dB cos theta. Since I took the angle with y-axis itself, then that becomes dB cos theta, which is mu naught cos theta di by 2 pi r. Now we'll need to integrate this. But imagine integrating this. You are integrating with respect to current, but theta is a variable here. Okay, do you agree with that or not? This current di, the blue one, you observe the second diagram, it creates dB in this direction. Some other current, let's say the yellow one, it creates magnetic field this way. Then it will make a different angle. You consider one more current if you want. Say that green one. Yeah, the green one was creating a magnetic field this way. So we visualized that already. Different dBs are in different directions. So theta is a variable from dB to dB. And you can't have two variables, or you can't have variable as theta but integrate with respect to current I. So can any of you tell me a way to proceed?
Sir, DL is equals to R d theta.
Good. DL is equal to R d theta. But what to do after that? Okay, listen. So what you all need to do is, see, you have to convert the integral to a single variable, not two variables. So we'll try to express di. Di is what? One small stream of current. We'll try to express that in terms of d theta. Okay, so for that we'll need to do some visualization. See, di is flowing along this path. You see the diagram on the left side. Okay, it's flowing along the wall of that hollow cylinder within that width. Right? If you visualize it in the second diagram, it's like di is flowing within this angle. You can call this angle as, can we call this as d theta? We'll make some adjustment here. Let's take this angle as theta. Then this can be taken t theta. And if that angle is theta, this becomes 90 minus theta. So the component in the y direction becomes dB cos 90 minus theta, that is sin theta. That adjustment I'm making, just to avoid confusion. So di is the current enclosed in that angle d theta. You can say enclosed is not the proper word. It's not being covered by anything. It's the current within that angle d theta. Are you all convinced with this or not? Any doubt in this? Okay. Now we need to relate them. Yes, said dl is equal to r d theta. So that way you can relate the length to the angle. That is also reasonable. Let's directly relate current to the angle. So the total current flowing on this surface is I. Okay. The current I is spread over this angle of how much? 180 degrees. That is pi radians. Current I corresponds to pi radians. Di corresponds to d theta. Divide them. Okay. Or you can do second divided by first. You get di by I is equal to d theta by pi. So di becomes I d theta divided by pi. That's the current in the angle d theta. Okay, in the part of the surface which subtends an angle d theta, you can say. Yes, Isha and Shashank, is this point clear?
Yes, sir.
Okay. And from here, I think you can solve. You get the y component this way, dB sine theta. No, dB was mu naught di by 2 pi r and y component, so sine theta. Now in place of di, you will write I into d theta divided by pi. So in place of di, you write I d theta by pi, and you just have to integrate this with proper limits. Integrating sine theta is easy only. Do that, you will get the net field. This is somewhat similar, let me say, to electric field at the center of a semicircular ring. I think we have done that problem also in class. We took a semicircular ring having charge uniformly distributed. We found the net field at the center. So there we use Coulomb's law to write the expression for field produced by one element. And after that, the steps are similar. Okay. Next question. Next question I'll not solve completely, but if you get the picture, then if you get the idea, then I think you'll be able to solve. Just a moment. Yeah. So you can see there is a flat sheet carrying current in a particular direction. So here also there are like many streams of current. This is one stream of current, another stream of current, and so on. Infinite streams of current are there. They're all straight. They're all infinitely long. You have to find out the net field at some point in front of the sheet. So can one of you tell me the steps? Any idea how to proceed? And in the last two questions, it was a cylindrical surface, curved surface. Here it's a straight surface. That's all. What can be done?
Take a single line of current.
Okay. Consider one stream of current, maybe this one. Okay, just a moment. Let me highlight that. So in this element, there will be some current flowing. Yeah, after that.
Calculate the magnetic field at field.
Okay, you have to express the magnetic field produced by that stream of current, that small current at this point. So a little bit of visualization is needed. You'll have to apply the right hand thumb rule. The thumb will be along the current. Fingers will be towards the point P. Then situation will be like this. I'll just draw it roughly. Thumb in the direction of the current and fingers this way towards P. Then palm you will see will be facing somewhat like this. Okay, so the direction of magnetic field produced by this current, you'll have to effectively join this point on the z-axis to this point P. The field will be in this direction. Okay, let me draw it in red itself. So that element will produce a magnetic field this way, dB. Okay, similarly, you'll have to consider other elements as well. There'll be one stream of current along the y-axis, exactly along the y-axis. Yash, can you tell me the direction of magnetic field produced by this current at the point P?
Sir, is it passing through origin?
The current is passing through origin, yes.
So if I take my thumb like pointing on y-axis and my fingers towards that point, it will be parallel to the minus z-axis.
Parallel to negative z, correct. So that element will produce a magnetic field this way. Okay, just a moment. Parallel to negative z, so it should be like this. Yeah. One magnetic field like this. Let's consider some more elements, maybe on this side. Thumb along this blue current and fingers towards the point P, the magnetic field will be this way. Hope you all are able to visualize that. If you have any doubt, you can ask. So there'll be a bunch of magnetic field vectors. And see, this sheet extends up to infinity like this also. Okay, so you'll get a bunch of magnetic field vectors in many different directions like this. What is the resultant direction of all these magnetic fields?
The yellow vector, sir.
The yellow vector, negative z direction. Let us take the top view, it will become clear. So if you look at this sheet from above, just a moment. It appears like a straight line, but current is not flowing along that line. Current is flowing perpendicular to that line. So if you see from above, yeah, it's like there are many streams of current. You're looking from above means you are on the positive y-axis. You are on the positive y-axis, and the point where we want the magnetic field is on the positive x-axis. That is clear from the diagram also. This is where we want the magnetic field, and this is the positive z direction. Towards you is the positive y direction. This is positive x. Okay, so the red element we took, red current we took, is somewhere here. If you join that to this point P, it creates a magnetic field this way. We are going to consider this one to solve the problem. Okay, but we know the net field is going to be in the y direction. So similar procedure, you'll have to write an expression for dB, then take dB's y component, and then integrate dB's y component to get the net magnetic field. Okay, let us take the next step. These are all straight currents. We know the formula for magnetic field produced by a straight infinite current, mu naught I by 2 pi x. So tell me, how should we write dB now? Can we write the total current I? Or what is the current in that element or in that section that we have considered? Clearly the current is dI. So dB becomes mu naught dI divided by 2 pi. In the formula, x is the distance from the current wire to the point where you want the magnetic field. In this question, how will you express that distance? What is the distance from the current to the point where you want the magnetic field? Anyone?
Sir, it will be like the hypotenuse.
What are the sides? How much is this distance?
It is A, sir.
That is A from the question. The point where you are asked to calculate the magnetic field is A, 0, 0. So this distance is A. How much is this distance?
Y, sir.
Z. Towards U is the y-axis. Okay, the sheet is along the z-axis, as you can see. Okay, in that diagram also I will show this distance is the z coordinate. Okay, is this clear to all of you? Any question if you have, you can ask. So this is z, that side is a, then this becomes root of a square plus z square. Z being a variable from current to current. Okay, so 2 pi root a square plus z square. As you can see, from current to current, that z value will change. Z is a variable. Then, okay, let us first take the y component. After that, we'll see what else can be done, what else should be done. Let's call this inside angle as theta. See, these are all like mathematically tough also to do. Call this angle theta, then this becomes 90 minus theta, then this again becomes theta. Right. So y component becomes dB cos theta. From that right angle triangle, how much is cos theta?
A by root of a square plus z square.
A by root of a square plus z square. If you do that, dB's y component becomes mu naught di. Okay, you are going to multiply this with a by root of a square plus z square. So mu naught di a divided by 2 pi a square plus z square. That's the y component, and now you'll have to integrate this. Can we integrate it directly, or do we need to make any adjustments?
We need to adjust since z is also a variable.
From one current to the other, the z coordinate changes. So you'll have to write di in terms of dz, and for that, to help you with that, this is already given. Di is simply lambda dz. Use it directly there, and then you use some integration by substitution or whatever methods of integration you know to do that. Limits will be from z is equal to minus infinity to z is equal to plus infinity. Okay, because it's an infinitely large sheet. Okay, that way. Okay, then the last question, just a moment. Actually, these are all quite lengthy. That's why I gave only 4 questions. And for this, I kind of gave a hint in the last class also. Just a moment. Yeah. So there is a coil wound like this. It's a planar coil only, but it's like squares. The wire carries a current I as indicated in the diagram. Inner length is A, outer length is 2A. You have to find out the net magnetic field at the center. Okay, think of an idea, all of you. I'll give you 2 minutes. What can be done? See, it's a coil, fine. But can you think of it as some system whose magnetic field we already know? As a collection of some systems whose magnetic field we already know? What does it look like?
Collection of square loop.
Collection of
Square loops.
square loops. Do you know the magnetic field inside at the center of a square loop?
Is it just 4 into mu naught I by 2 pi into a by 2?
Can you repeat? 4 into
4 into mu naught I by 2 pi a by 2.
no.
Pi a basically.
These are not infinite wires.
Oh,
Okay. See, even if you want to find the magnetic field at the center of a square loop, you'll have to treat the square as a collection of 4 straight wires. Okay. We did one question based on
yeah.
equilateral triangle, right? So
And then
yeah,
it gets multiplied with root 2 cos 45 plus cos 45.
the angle is also important, right? So what we will do is we'll take one straight wire, okay, somewhere along this. So let me mark it like this. Let's take one straight wire like this, randomly somewhere in between. Current is flowing anti-clockwise. So in this straight wire, the current will be flowing up. Okay. Now see, this is a coil, right? If the current in the wire is I, then every single line will have a current I here. So if you consider this yellow one as a single line, then it means its current is I. It means the current flowing in it is I. Okay. Assume it is at some random distance. Why assume distances and all? Because we need to find its magnetic field at the center. Okay. So let's say the distance from that wire to the center is some x. X is a variable, of course. And if you connect the point to the ends of the wire, why connect the point to the ends of the wire? Because we need magnetic field of a finite wire. This angle will be 45 degrees. At the other end also, the angle will be 45 degrees itself. Okay. So if the current is I, then we can write the magnetic field of one wire as mu naught I by 4 pi. The distance x is unknown. It's a variable. Cos 45 plus cos 45, 1 by root 2 plus 1 by root 2 becomes root 2. So field due to one straight wire is mu naught I root 2. Okay, that root 2, okay, let's keep it as it is for now, divided by 4 pi x. But we need the total magnetic field. What can be done? Can you just multiply this with, what do you say? Can you just multiply this with 4 such that you cover a square like this at the distance x? Because for each distance you can get a square. So this square will be at a distance x. So you found field due to, we wrote expression for field due to one wire, no? One straight part. Multiply with 4, you'll get field due to that square. And can you just integrate it?
Sir, we need an dx term in that.
Good. Okay. This we had discussed in the last class also, an idea related to this. See, in one wire, this is the field. Fine. And with each wire, you can say there is a square being formed. So B net due to one wire will be 4 times of field due to one side of the wire. So 4 get cancelled. You get mu naught I root 2 by pi x. But if you want the net field due to the entire wire, all the squares, you'll have to integrate all the squares. You will have to integrate field produced by all the squares. So you'll end up integrating mu naught I root 2 by pi x. In this, there is no dx or di or anything. And if there's nothing like that, the integration will tend to infinity, which is not correct. There are a finite number of turns. The length of the wire is finite. The field produced by it should be finite. Okay. So yeah, as Yash correctly recollected, we should somehow get a di or a dx term into this. So what we do is, we don't take each wire. Okay, we take a certain region. If that distance is x, then this region or this strip, you can assume, has a thickness dx. Yeah, I'll write it on the side. This thickness of the strip, yellow strip that is there, you can call it dx. Now still, how to get di into that? Each wire has a current I, and you are given in the question that there are n loops. Means on each side of the frame there are n wires. Okay, n wires are placed within what distance? Now see, that inner side is a, that means half of it is a by 2. So from here to here, okay, I'll use some other color, pink. Okay, from here to here is a by 2, and from here to here is 2a divided by 2, that is a. That means this distance is a minus a by 2, that is a by 2. So the square frame that you see, each border of that frame has a width of a by 2, and in that width of a by 2 there are n turns or n wires. Okay, in a width of a by 2, if there are n wires, then in a width of dx, you can assume there are dn number of wires. Divide these two equations, you get dn by n is equal to dx by a by 2. 2 goes to the numerator, you can write it as 2 by a. Therefore, dn, the number of wires in that width dx, becomes 2 capital N dx divided by a. Each wire has a current I. Therefore, the current in that width dx will become current in each wire multiplied with the number of wires. That becomes 2n I dx divided by a. So that's the current in that width. And we got it in terms of dx. We will now put this in the expression for magnetic field and then integrate from lower limit of x to upper limit of x, we'll get the answer. Okay, I'll send you this like a copy of today's notes. Go through it, solve all these problems once again on your own. Okay, this practice you definitely need to calculate magnetic fields produced by straight wires. I'll try to make some more questions also and send you another worksheet. So today we'll not be discussing Ampere's law, it will take time. So tomorrow morning itself, I'll send you some more questions based on magnetic fields produced by straight wires and curved wires like arcs. Okay. Practice more, then next class, maybe Thursday. Yeah, Thursday we'll discuss Ampere's law.